In this video, we're going to tackle horizontal asymptotes of rational functions. We're already familiar with vertical asymptotes, so these are obviously going to be going the other direction, right? To introduce this idea, I want to consider a problem about turkeys, since it is Thanksgiving season, more or less. So this is what turkeys look like, in case you're unfamiliar. I had to Google this, but they eat nuts and fruit and bugs. And we can imagine, right, that there's only so many turkeys that can live in a particular area of the forest, right? So there's only so many pieces of fruit or seeds or nuts or whatever they're eating to go around, right? So that's what this problem is about, is what seems to be the number of turkeys that can survive in the forest, okay? So here's a rational function f of x that models the number of turkeys, and we're going to use the graph of this function to answer our question. So I've already graphed it on Desmos. I'll show you what that looks like. So here that is, and notice I put parentheses around the top to get a fraction. So I'm dividing the whole top by the bottom. You have to do that on your graphing calculator as well. And I'm going to scroll over. I just care about positive time and positive turkeys. I don't care about negative 20 years because that doesn't make a whole lot of sense, right? So here is my graph of f of x. And notice we start with about 1,000 turkeys. So every one x is 1,000 turkeys. Then we decrease for a little bit, and then we sort of climb back up, right? And as time goes on, notice no matter how far I scroll to the right, we're kind of leveling off, right? And my y values are slowly getting bigger, but they're really just getting closer and closer to 5, right? So let's take a second to sketch that on our little graph on our notes, right? So we had what seems to be what we'll call a horizontal asymptote at 5, right? So I'm going to draw that in first, y equals 5. And then we started at 1, and our scale is not going to be very accurate, but we want a curve that just kind of snuggles up to that line y equals 5 and kind of runs parallel to it. Okay, so that's our horizontal asymptote. And the definition of a horizontal asymptote is, well, exactly what it looks like here, right? It's this horizontal line that the graph approaches but never touches, okay? And in this context, that horizontal line is the maximum number of turkeys that we can have in the forest, okay? In environmental science, there's this idea of carrying capacity. It's the carrying capacity of the forest. It's the maximum number that can survive there, okay? So the answer to our question here, based on the graph, remember the population is in thousands, okay? So the answer here would be 5,000 turkeys based on that horizontal asymptote. And where does this value seem to show up in the function? This is a little bit trickier, right? So notice the degree of the numerator and the denominator, they're the same, right? So we have an x squared and an x squared. So remember, degree is just the highest power of x that shows up in a polynomial. So you should know that from Algebra 2. And the leading coefficient is the coefficient of that degree. So 5x squared, the leading coefficient, or the coefficient of 5x squared is 5. X squared, the coefficient is 1. So now notice, if we zero in on just the leading coefficients, just the highest powers of x, we have 5x squared on top over, well, plain old x squared is really a 1x squared on the bottom. And the result there is 5, which is the same as our horizontal asymptote. So the answer to this, where does the value show up, is that it's the ratio of the leading coefficients, right? So what happens is, as x gets really large, time goes on, it doesn't matter so much that there's a 50 in the denominator or a 50 in the 12x in the numerator, because x squared grows way faster. And as x gets really large, the y values of this function approach 5 over 1. Now, if this was a 10x squared on top and a 1x squared on the bottom, our horizontal asymptote would be at 10. If it was a 20x squared on top and a 5x squared on the bottom, our horizontal asymptote would be at 4. Okay? The ratio of the leading coefficients determines this thing. Now in this case, we had equal powers of x, right? So we have x squared and x squared. What if they were different, right? So here's another case. We have x squared minus 9 over x plus 10. So notice we have x squared on top and x on the bottom. I've given you here the graph of f. So here, the numerator has a bigger power than the denominator. So we'd say this has, obviously based on the graph, it grows forever. No horizontal asymptote. And that's because the numerator is bigger than the denominator. So the top of our fraction grows faster than the bottom, meaning overall our function continues to grow. Then function number 3, this is the opposite case. So notice I have an x on top, and then my leading term on the bottom is a 2x cubed. So looking at this graph, it's a little hard to see, but notice my graph really never leaves the x-axis. So this one we would say has a horizontal asymptote at y equals 0. And that's because when the bottom of a fraction gets bigger than the top, the fraction gets smaller. So if overall the fraction is growing much faster on the bottom, the function gets closer and closer to 0. Okay, so our main idea here is that the degree of the numerator and the degree of the denominator determine where these horizontal asymptotes are. So if b is bigger than a in case number 1, meaning the exponent on the bottom is bigger than the one on the top, the fraction we'd say is bottom heavy. Bottom's growing faster. And the horizontal asymptote is y equals 0, right? So that was case number 3 here. So an example, and you can make up an example of your own if you think you understand what I'm saying here, would be, I don't know, x plus 1, or let's say x plus 5. My brain decided, right? Over x squared plus 1. So 2 is a bigger exponent than this 1 here, imaginary 1, right? And that gives an horizontal asymptote at y equals 0. If the exponents are the same, then the horizontal asymptote is at the ratio of the leading coefficient. So in this little example here, it would be at c over d. And that's because the x's cancel, right? So an example here would be 5x to the 5th over 2x to the 3rd plus 6x to the 5th. So the 2x to the 3rd does not matter. We care only about the 5 and the 6 here. So our horizontal asymptote would be at y equals 5 over 6. All right, and our last example, if the top is bigger, so a is bigger than b, the fraction is top heavy. The top is growing faster than the bottom. Then the horizontal asymptote does not exist. So an example, any example where the top is bigger than the bottom works here. X to the 85th over x would have no horizontal asymptotes. Okay. So that's the key idea here. The second page of the notes will be an example that you can copy down from Delta Math, but make sure your notes are complete before you move on to that.